Tonight's lecture deals with science method. This is module 1.2 in your book, beginning on page 22. In the winter of 2007, David Blayhart, chief of the Wildlife Disease Diagnostic Labs at the National Wildlife Health Center, received a very troubling phone call from his colleague, Alan Hicks. Hicks is a biologist tasked with surveying, among other things, bat populations in New York State. This year, they found a big problem. There were thousands of bats dead at several different sites and a near-total colony collapse at some of them. But the bats hadn't merely died, they also suffered, and badly. Their skin was so dry and flaking, and their bodies were so emaciated that bones pushed easily through the skin. Many of them were found at the cave opening, a sign that they had been roused from their hibernation and had been looking for insects to replenish their fat stores. Of course, because it was the dead of winter, there were no insects to be found. Before long, surveyors across the region were reporting similar troubles, including cases where entire colonies had died. Nobody knew what was killing the bats, but because most biologists noted a peculiar white fuzz on the victims' muzzles, the mystery affliction earned the moniker white nose syndrome. In the next years, white nose syndrome spread rapidly, reaching 37 states and 5 Canadian provinces. It has infected at least 7 different species of bat and is driving at least 2 of them to the edge of extinction. Researchers estimate that more than 6 million bats have died from the disease. For scientists like Blayhart, those grim numbers would fuel a race against time to answer 2 urgent questions. What is causing the disease, and can it be stopped? And on this slide, we see what the effect of white nose syndrome looks like on the bat's muzzle. And when we move to this slide, we see what it's doing to their wings. And that brings us to our key concept number 1. Scientists investigate the natural world using a transparent method of inquiry, and their findings are evaluated by other science. So science is both a body of knowledge, that is basic facts and complex explanations, and it is also the process used to get that knowledge. The body of knowledge part of science is ever-changing. Facts, figures, and understandings are revised as scientists learn more about any given topic through their research using the quote-unquote process of science. This powerful process enables us to test our ideas by gathering evidence and then to evaluate the quality of that evidence. The scientific method is based on empirical observations, that is, information about physical phenomenon that can be detected with the 5 senses or with equipment used to extend those senses like microscopes or sonar. For that reason, only phenomena that can be objectively observed, that is, the observation can be verified by anyone in the same place using the same equipment, are fair game for science. Phenomena that are not objectively observable, which would include questions like, is the death penalty wrong? What is the meaning of life? Cannot be empirically studied and therefore are not within the purview of science. Those type of questions fall under what we call ethics. Like any good scientist would do, Blayhart and his colleagues applied the scientific method to solve the mystery of the dying bats. They worked logically from previous knowledge and observations of the natural world toward new questions and possible answers. They started with observations, thousands of dead bats and a mysterious white fuzz on most of their noses. They combined these observations with existing knowledge to make some inferences, that is, explanations of what else might be true. Because bats hibernate in cold, dark, wet places, the kind of places where fungi also thrive, they inferred that the fuzz was a fungus, and because most of the bats that died had it on their noses and body, they inferred that it was somehow related to the deaths. Next, they gathered some evidence to investigate these inferences. Samples of the white fuzz were collected and identified in the lab as a fungus. Scientists eventually came to identify it as Pseudogymnoascus destructans. It was an obscure little fungus that hardly anyone even knew existed, and it was part of a family that was not known to be pathogenic at all. So was this fungus causing the bat deaths? If so, where did it come from? To begin answering those questions, researchers studying the problem would need to generate some hypotheses. A hypothesis is a proposed answer to some research question, an inference, a guess based on previous knowledge and current observations. Researchers had no trouble coming up with the hypotheses, including these two. The white nose infection caused by the fungus was secondary and opportunistic. It had always been present, but was only able to grow on the bats because their defenses had been weakened by another pathogen. Another hypothesis they came up with was that the fungus was new to the region. It had been transported from some other place. To figure out if these ideas were correct, they would have to test each one. To test a hypothesis, a researcher designs a scientific study and makes an experimental prediction, a statement that identifies what is expected to happen if the hypothesis is being tested correctly. A scientific study must be designed to be a quote-unquote fair test. This means the results of the test could support or falsify the prediction. Even if evidence repeatedly falsifies an experimental prediction, the hypothesis is rejected and alternative hypotheses can be tested. If a hypothesis is supported, researchers repeat the study to validate the data and generate new predictions that test the same hypothesis from every different angle. As supporting evidence mounts from replicate studies and from multiple predictions, we become more confident in our data and our conclusions. But before being published, scientific reports are subjected to what we call peer review. In other words, they are reviewed by a group of third-party experts. Studies that are not well designed or conducted are not accepted for publication. Therefore, peer-reviewed published research represents high-quality scholarship in the field. This process might slow down the dissemination of information, but adds a needed check on the validity of that information. There are even formal processes for the retraction of a study that has come into question after publication. And that brings us to our infographic number 1 on page 25. Scientists work from observations and previous knowledge to ask new questions and pose possible answers to those questions. They test the hypotheses by generating a testable prediction and designing a study to test that prediction. Evidence is collected, evaluated, and shared, generating new predictions and sometimes new hypotheses, making this an ongoing process that allows researchers to delve deeper and deeper, building on previous studies to gain new knowledge. So we never prove anything right. We only prove stuff wrong. Because in the future, there could be a wider range of experiments, you could compute a wider range of consequences, and you may discover that the thing is wrong. And that brings us to our key concept number 2. Scientific certainty increases as evidence mounts and can be quite strong, but science never claims or even expects that its research will reach a level of absolute, unquestionable proof because there are always new questions to ask and new experiments to perform. So hypothesis testing is at the heart of science. For example, Blayart's team investigated the hypothesis that the fungal infection was opportunistic and the bats were already weakened from another infection. Close examination of internal organs such as the liver, heart, lungs, and kidneys did not reveal any abnormalities, no sign of a problem or previously undetected infection that would make the bats more susceptible to the fungus. The skin infections caused by the white nose syndrome were occurring in the absence of other infections. The opportunistic hypothesis was then rejected and scientists moved on. Meanwhile, as the word of the colossal bat die-off spread throughout the scientific community, researchers in Europe and China identified the same fungus in their bat caves, only the bats were perfectly healthy. It appears that Pseudogymnoascus destructans, or PD, had been native to those regions for a very long time. Because the bats in those areas had evolved with the fungus, they likely had adaptations to help them survive the infections. Scientists are currently investigating the nature of these adaptations to determine why European and Asian bats do not succumb to this disease. This new information lent some weight to the second hypothesis about the origin of the fungus, that it had been brought to North America from elsewhere, and we call this the novel pathogen hypothesis. The fact that the fungus is found in the dirt of infected caves and on clothing and equipment from cavers who visit these caves suggests a means of transport from cave to cave. When evidence mounts like this to support a given hypothesis, scientists suspect they are on the right track. But even then, they don't stop. All conclusions in science are considered tentative and open to revision because our understanding of a concept or process may change as more observations and evidence are gathered. That is not to say that all conclusions are equally valid. There are degrees of certainty in science. We know some things better than others. The more evidence we have in support of an idea, especially from different lines of investigation in which the hypothesis is tested in many different ways, not just tested the same way repeatedly, the more certain we are that we are on the right track. So, if a hypothesis survives repeated testing by numerous research teams and in numerous ways, it may be incorporated into a theory. That is a widely accepted explanation that has been extensively and rigorously tested. However, in keeping with the tentative nature of science, even a well-substantiated theory is open to further study and can be revised sometimes significantly. That is, if the new data strongly supports new conclusions. For this reason, scientists do not expect or require a quote-unquote absolute or unquestionable proof for their conclusions and explanations. This is, in fact, not possible because there are always new questions to ask and new ways to investigate those questions. And this is not a weakness. It is a way to strengthen our understanding of a topic and uncover new questions and continually add and revise the body of knowledge that is science. This definition differs significantly from the lay use of the word theory, which typically refers to a speculative idea without much substance. Non-scientists, include some politicians, have been known to dismiss some scientific theories as quote-unquote just a theory, by which they mean this is unproven and therefore we shouldn't have to consider it. But that line of thinking represents a serious misunderstanding of what a scientific theory really is. Next to a law in science, theories in science represent the highest level of certainty assigned to an explanation. They should not be rejected without substantial scientific evidence to the contrary. When it came to the bat die-offs, scientists were nowhere near a theory, but they did have enough information to hypothesize further. Since bats don't travel across oceans, the fungus was probably introduced to U.S. caves by humans, most likely cave explorers who carried fungal spores overseas on their clothing and gear, and then spread to multiple colonies by bat-to-bat contact. Scientists collected more data from the bat caves and bat carcasses. The cold-adapted fungus seemed to thrive on hibernating bats, but it did not appear to affect active bats. Researchers suspected bats were easier prey for the fungus during hibernation because in that state, their body temperatures were lower than normal and their immune systems were suppressed. In active or awake bats, the fungus's growth would be slower because those bats were warmer and their immune systems were fully active and could fight off the infection. During hibernation, bats are in a state of inactivity, conserving energy by reducing their metabolic rate and body temperature. Bats will occasionally rouse from this inactive state to drink water and excrete waste. These arousals take a lot of energy, but bats normally have just enough energy or fat stores saved up to get them through 8 to 12 arousal periods. Examination of infected bats revealed that the fungus appeared to attack the hairless areas, namely the wings, ears, and noses, areas vital to the bat's ability to maintain body temperatures during hibernation. Because bats with white nose syndrome appeared to die of starvation, Blehart and others hypothesized that the fungal infection was causing them to rouse more often and thus burn up their fat reserves too early in the season. They would scurry to the cave openings in search of insects to eat, but in the dead of winter, none would come. Without insect meals to replenish their stores, they would starve to death before spring arrived. And that brings us to our infographic number 2 on page 27. There are degrees of certainty in science. We know some ideas are better than others. The more evidence we have in support of an idea, especially when the evidence comes from different lines of inquiry, the more certain we are that we are on the right track. But since all scientific information is open to further evaluation, we do not expect or require absolute proof. And that brings us to key concept 3. Experimental studies manipulate conditions, whereas observational studies collect data without intentionally altering any conditions. Each supplies different lines of evidence for analysis. So with evidence mounting that an introduced fungus from overseas was indeed responsible for the bat die-offs, scientists still needed to test the hypothesis that death was caused by arousing too often and using up fat stores before the end of winter and before the return of insects. To do this, a research team led by Bucknell University biologist Deanne Reeder attached temperature-sensitive data loggers to the backs of 504 free-ranging little brown bats. By recording body temperature, these data loggers would tell the researchers how often a bat aroused during hibernation and how long it slept between arousals. At the end of the hibernation season, bats were recaptured and data loggers retrieved. For each bat, researchers noted if it was infected with white nose syndrome and whether it was alive or dead. Here's what they found. Infected bats aroused more frequently than healthy ones, and among those that were infected, the more tissue damage the bats had, the more often they woke. And the more often they woke, the more likely they were to die. Reeder's data logger study is an example of an observational study. This is one where scientists collect data in the real world without intentionally manipulating the subject of the study. They did not intentionally inoculate bats with white nose syndrome. They simply followed bats, measured a parameter of interest, and noted which bats were infected and which were not. In observational studies, researchers may simply gather data to learn about a system or phenomenon, like measuring the amount of carbon dioxide in the atmosphere over time to see if it is rising or falling, or they may be comparing different groups or conditions found in nature, like monitoring asthma cases in areas with high and low air pollution. These types of studies are very useful in environmental science because they enable us to look at whole systems that cannot be manipulated in a lab or field setting. On the other hand, experimental studies, by contrast, involve intentional manipulation of experimental conditions. A factor that is changed is called a variable, such as whether test subjects are exposed to a pathogen. Specifically, scientists manipulate the independent variable and measure the dependent variable to see if it's affected. So these types of studies rely on test groups and control groups. The test group subjects are exposed to a variable that scientists want to study, and the results are compared to a control group that was not exposed to the variable or was exposed to the variable to a different degree. Ideally, all other factors remain the same, such as temperature or light exposure. These are called constants. Observational studies can also have independent and dependent variables as well as control and test groups. For example, control bats in the study that we have been talking about were collected from a site with no white nose syndrome and compared to test bats from sites where the disease was found. So, in an example of another experimental study, another team of researchers at the University of Winnipeg deliberately inoculated bats with a solution containing PD. Control bats were given a sham inoculation containing the solution but no PD to determine whether the fungus affected the length of the bat's sleep periods during hibernation. So the independent variable is the type of exposure, and the dependent variable is the length of sleep periods. The results showed that bats that had been intentionally exposed to PD experienced shorter sleep bouts because they woke up more often than control bats, providing evidence that PD infections did interfere with hibernation. Studies of this type must pass ethical review before beginning in order to ensure animals do not experience undue pain or stress. However, animal studies of any type raise ethical concerns. When scientists choose between experimental studies like this one or observational studies that do not pose a potentially harmful manipulation, they weigh the ethics of intentionally making animals or people sick against the benefits that the research might bring, such as finding a cure for a disease or its cause. So, as mentioned earlier, in science there are degrees of certainty. We know some things better than others. These degrees of certainty are expressed in terms of probabilities with a branch of mathematics called statistics. Once data are collected from an observational or experimental study, statistical analysis is done to calculate the probability that the variable being tested influenced the results. Specifically, it calculates the likelihood that any difference observed between two groups is just a result of natural variation, for instance, not statistically significant, or if it represents a genuine difference between the groups, the differences are considered statistically significant. In Reader's study, for example, average sleep periods were longer in groups of bats without white nose syndrome compared to survivors who had white nose syndrome, but these differences were not enough to be statistically significant, so we conclude that there is no difference in the duration of sleep periods between these two groups. However, sleep periods were statistically shorter for bats who died of white nose syndrome, so we can conclude that white nose syndrome in these bats did increase arousals later in hibernation compared to uninfected bats or white nose syndrome bats that survived. And that brings us to our infographic number 3 on page 29. Scientists collect evidence to test ideas. Moving on, experimental studies are used when the test subjects can be intentionally manipulated, and observational studies allow scientists to look at entire ecosystems or other complex systems. Both can be used to test the same hypothesis. And that brings us to key concept number 4. Two events that occur together are correlated, but this does not necessarily mean one caused the other or even that they were related in a meaningful way. A scientific analysis of an environmental problem provides the information necessary to determine what policy, if any, is needed to address that issue. Observational and experimental studies differ not only in their approach, but also in the type of information they ultimately provide. Winnie Frick and her team at Boston University conducted an observational study that compared bat colony sizes over time in areas with and without white nose syndrome. They observed a sharp decline in colony size, but only in the colony experiencing white nose syndrome infections. Observational studies like this reveal correlations. That is, they can show that two things occur together. A colony was somehow exposed to white nose syndrome, and most bats in that colony died shortly thereafter. But observational studies can't necessarily tell us if one thing caused the other, or even if the two factors are related in a meaningful way, because it could just be a coincidence. Perhaps something else wasn't evaluated that caused the die-off. So although scientists suspected from the very start that the white fuzz was related to the bat die-offs, they needed more evidence to determine whether the two events were connected in a cause and effect relationship. For that, they needed experimental studies that intentionally exposed bats to fungus. If all other factors are the same between the two groups except the one variable that is manipulated, in this case exposure to the fungus, and we see differences in the dependent variable that we are monitoring, then it is reasonable to conclude that the manipulation caused the effect. It is important to understand that while experimental evidence is generally considered stronger precisely because it can determine cause and effect, observational studies that amass a lot of evidence in support of a given correlation are also quite powerful. For example, we have only correlation evidence that smoking causes lung cancer in humans, but this relationship is not in question. In fact, observational studies that produce the same results as experimental studies offer particularly strong corroborating evidence. This is because they demonstrate the correlation between the variables even when the populations are exposed to many other factors that might influence the outcome. Conversely, when the results from observational studies do not agree with those from controlled experimental studies, we can conclude that other factors are probably at play. A scientific analysis of environmental problems provides the information needed to take the next step to determine that the problem needs to be addressed and how to go about doing so. So, when it is established that action is needed, the next step is to create a policy to deal with the problem. These policies need to be informed by science. To deal with white nose syndrome, the U.S. Fish and Wildlife Service drew from available research to create a national plan that addresses the disease. The plan lays out guidelines for a wide variety of actions, including disease surveillance and management procedures, as well as outreach programs to educate the public about the best practices and the need for containment. It has also closed some hibernation caves to the public in an effort to prevent humans from carrying fungal spores from one cave to another. Policies must also be flexible and able to adapt to new scientific findings. The U.S. Fish and Wildlife Service monitors bats and other species and can adjust the implementation of its policies as conditions change. Such adjustments include adding or removing species from the threatened or endangered species list if new threats emerge or their numbers increase. So, one dilemma faced by policymakers is the fact that gathering strong evidence about the cause of environmental problems takes time, sometimes longer than we can wait if we are to take meaningful action. This means policies often are based on incomplete data. For example, we don't know yet what the loss of bats would mean for the areas threatened, but it could be quite severe. Like most predators, bats are vital to their ecosystem. They are important predators of nocturnal insects like mosquitoes. In fact, every year bats provide billions of dollars worth of free pest control. Protecting them is good for their environment and many species that share it, including us. Acting sooner rather than later in the face of uncertainty is an example of applying the precautionary principle and may be the best way to avoid consequences that might be difficult to address if they occurred. Sadly, white nose syndrome is not the only threat bats face today. Worldwide, various bat populations are threatened by habitat disturbance and damage. Wind turbines, the bushmeat trade, climate change, and even fear and persecution from those who fear bats. But as with white nose syndrome, we need to use science to investigate the threats to determine if they warrant attention and, if so, how best to proceed. Scientists will continue to study the disease, possible treatment and prevention options, and the ecological impacts of bat declines, building on previous studies and pursuing new avenues of research that appear promising. Each new piece of information raises new questions that are addressed through the process of science. And that brings us to our infographic number 4 on page 31. Because they cannot control the extraneous variables in a research study, observational studies can provide correlation evidence that 2 or more factors are related. Experimental studies that can manipulate and control variables can establish whether a cause and effect relationship exists. And that brings us to our key concept, number 5. Published information about scientific topics abounds in our modern world. Information literacy skills can help individuals determine the reliability of that information. Understanding how scientists study the natural world and ask questions allows us to apply the scientific method to investigate a question. But most often, we will be evaluating the research of others, and this means we need to be able to distinguish between reliable and unreliable sources of information. This is a skill known as information literacy. It's the key to drawing reasonable, evidence-based conclusions about any given issue or topic. It is especially important in public health and science issues because when it comes to these issues, misinformation abounds, especially digital information that is readily available to most of us on our computers and smartphones. One of the first steps in information literacy is identifying what type of information source one is consulting. Is it a first-hand account from the original person or group that created or experienced it, or is it a retelling? So, our first choice for reliable information would be those that are called primary sources. Primary sources present original data or information, including novel scientific experiments and first-hand accounts of any given observation. Journal entries and interviews are primary information sources, as are research articles published in scientific journals. The research papers published by Reeder and Warnecke are primary sources. This means you can view the data or the evidence on which the researchers base their conclusions and evaluate it yourself. But most of us start a step or two lower than primary sources. Perhaps it is a newspaper article about some recent research or event, or a video we see on television or online. This information may be coming from a secondary source, one that presents and interprets information solely from primary sources, such as a science journalist who reviews a recent research article. Moving on, but most likely, our initial information comes from tertiary sources. Tertiary sources are those that use one or more secondary source. Most books, including textbooks and reports from the popular press, are tertiary sources. Most blogs, websites, and news shows that provide additional commentary or foster debate also qualify as tertiary sources. But because tertiary references do not consult the primary information source, they may perpetuate errors made by a secondary source. For this reason, they are less dependable than secondary sources or primary sources. That is not to say that secondary and tertiary sources are not useful. They are a good starting place. But if you have unanswered questions, or if there are inconsistencies in the reports you encounter, going back to the primary source is the best way to reconcile those differences or find answers to unanswered questions. For any claim you encounter, you should be asking, what's the evidence for that claim? Where do you find that evidence? Do you find that evidence in primary sources? Information literacy in the digital age must be expanded to include media literacy. That is, the ability to evaluate digital sources of information. The ease of publishing information digitally and the lack of any oversight for many pieces of digital information means that we all need to have the skills to determine the veracity of a piece of information. Information and media literacy skills allow us to identify information presented under the guise of news that is misleading in some way. Questionable quote-unquote news has been around a long time. Today it comes in a variety of forms. Fake news is false information. In a digital format, it may be what we call clickbait. Clickbait is a shocking title to get us to click onto a story. Clickbait is common on websites where authors make money based on how often the link to that story is opened. Second is misleading news. Misleading news contains some truth but may be incomplete or out of context and or contain false information. It is often presented to support an agenda. For instance, political propaganda often falls under this category. Then there is satire. Satire is intentionally outrageous. It may take some investigation to determine if the story is offered as legitimate news or as a satirical commentary. Moving on, satirical news outlets like The Onion deliberately present news in an outrageous fashion using humor, irony, and exaggeration. The story may be for entertainment only, or its intention may be to expose what the author sees as corruption or irresponsible actions. Political satire is seen as an important part of democracy and a way to broach difficult or even taboo topics. A reader must be diligent when trying to determine the credibility of a news story. Tips for ferreting out questionable news are offered in infographic 5 on page 34 of your book. More and more people are getting their news from digital sources, including social media, but this news may not be authentic or reliable. It may even be intentionally fabricated, but presented in a way to fool the reader. To evaluate the readability of any news story, there are some basic questions you can ask to help navigate the world of digital news. And that brings us to key concept number 6. Evaluating a claim requires critical thinking skills. Always ask for the evidence and evaluate it. Look out for logical fallacies and keep an open mind. Also, be willing to go where the evidence leads you. Information on environmental issues abounds, and it is our responsibility to determine which information sources and arguments are sound and which are faulty or out of date. While how best to deal with white nose syndrome in bats may not be a hot topic on the minds of most people, many other environmental problems make headlines daily and are the subject of a heated debate. For instance, should coal be phased out, or is it still a vital lifeline needed by workers in coal-producing states? How should we respond to climate change on an individual or national level? Is the added expense of water or air pollution prevention worth its costs? Search long enough, and you will find arguments on many sides of each of these and other environmental questions. Sorting through the rhetoric of any complex environmental problem requires diligence and the use of critical thinking skills that allow one to logically evaluate the evidence. The same skills are used by scientists to evaluate scientific studies. An evaluation of any argument or claim should include an evaluation of the logic that underlies that claim. Is it supported by evidence? In some cases, the way a claim is stated can be misleading. This may be intentional or the result of a poorly constructed argument. Literacy devices used to confuse or sway the audience to accept a claim or position in the absence of evidence or by twisting the evidence are referred to as logical fallacies. For example, if bat conservationists had called for the immediate closure of all U.S. caves that housed bats after the 2007 discovery of so many dead bats at Howe's Cave, they would have been guilty of hasty generalization. At that point in time, it was too early to know what was causing the deaths or if it could be transmitted to other caves. Logical fallacies can persuade others to accept a conclusion or to doubt one. Industry, for example, has been found to deliberately mislead consumers in order to make sales. Perhaps that comes as no surprise. After all, they are in the business of making money. But it is particularly disturbing when the products they sell are dangerous. For example, the tobacco industry argued for years that smoking cigarettes was safe and healthy, even though they had ample evidence from internal and external investigations that it was quite dangerous. To combat the growing mountain of evidence that smoking was linked to a number of serious health problems, the tobacco industry developed a playbook, that is, definitive steps that could be taken to confuse consumers. This included hiring scientists who would question studies that showed harm, in other words, they appeal to authority, and claiming that diseases like cancer and heart disease were too complex to pin any particular individual's ailment on smoking. This is an appeal to complexity. Also, ad hominem attacks, that is, discrediting the scientist or the physician personally, red herring statements, that is, extraneous information that is true but not relevant, and other logical fallacies were also used to sway the public and instill doubt that tobacco was dangerous. In one of their own internal memos, a public relations firm working for the tobacco industry stated, "Doubt is our product. If they could cast doubt on the science, they could delay regulation." And that brings us to infographic 6 on page 36 of your book. And this gives us a table of logical fallacies and some examples. Logical fallacies are arguments used to confuse or sway someone to accept a claim or position in the absence of evidence. So, critical thinking is the antidote to logical fallacies. It enables individuals to logically assess and reflect on information and reach their own conclusions. Critical thinking is a skill that can be broken down into a handful of tenets. First, be skeptical. Just like a good scientist, don't accept claims without evidence, even from an expert. This doesn't mean refusing to believe anything. It simply means requiring evidence before accepting a claim as reasonable, especially if it's counter to a well-established scientific consensus. Also, evaluate the evidence. Is the claim derived from anecdotal evidence, in other words, unscientific observations or single occurrences, or from scientific studies? If it is based on studies, how relevant are those studies to the claim? Were they done on human subjects or other species, intact organisms, or cells in a petri dish? Also, watch out for author biases. In the person or group making the claim trying to promote a position, is it financially tied to one conclusion or another? Is it trying to use evidence to support a predetermined conclusion? Also, always be open-minded. Try to identify your own biases or preconceived notions, and always be willing to follow the evidence wherever it takes you. Humanity faces many environmental problems today, from rising levels of greenhouse gases to water and air pollution to biodiversity loss and many others. That must be addressed if we are to reach the goal of living sustainably. It is vital that we base our policies on sound science rather than on speculation or what we would like to be true. Unfortunately, making logical decisions based on evidence, even when we have compelling evidence, may not be as easy as it sounds. Cognitive and social science research is revealing some interesting aspects regarding how the human brain operates. We would like to think that we are rational creatures weighing evidence to reach logical conclusions, but research shows that when presented with evidence that supports our current beliefs, this evidence tends to strengthen those beliefs. However, when presented with evidence that contradicts what we believe to be true, no matter how compelling, many of us simply reject it out of hand. To counter this quote-unquote confirmational bias, we must be willing to consider other viewpoints and, in doing so, look at the evidence and evaluate its veracity. If we approach new information knowing we may be biased to our current position, we may be more open to the evidence and be willing to go where the evidence takes us, just like a good scientist does. As information accumulates on the cause of the effects of white nose syndrome, a shift in the focus of researchers is taking place. Some bat researchers say research now focuses on breaking the cycle of infection and finding ways to stem the spread of the disease. There is even some evidence that the bats themselves may be showing signs of adapting to the fungus. One closely monitored population of Indiana bats has been observed to wake up together. Normally, arousal from hibernation is not a group behavior. This adaptation might help the bats expend less energy during arousal periods. More research is needed to elucidate how this behavior might help and if it is found in other populations or species of bats. Research on treatments is also underway. Studies revealing that the PD fungus is very sensitive to ultraviolet radiation have led researchers to begin testing its effectiveness as a potential treatment. And the results of experimental tests of a vaccine to white nose syndrome administered by injection or orally to treat bats are encouraging. 88% of vaccinated bats survived compared to only 30% of unvaccinated bats. Researchers hope to develop a spray-on version of the oral vaccine. Bats would ingest the vaccine during grooming. Another possible treatment came from a microbiologist at Georgia State University. This treatment showed that organic compounds produced by the bacterium Rhodocus rhodocorus reduce the amount of fungus that grows on bananas. This microbiologist teamed up with U.S. Forest Service scientists to test the idea in the field. Bats already infected with white nose syndrome were collected early in hibernation and briefly exposed to petri dishes containing the bacterium. At the end of the hibernation period, all 75 test bats were alive, although some still had wing damage from the fungus. Although it is too soon to know if the bacterial chemicals or any of the other treatments being tested will prove to be an effective treatment, teams of scientists are back in the lab and in the field trying to find out if there are still bats to treat. And that brings us to our core message for this chapter. The world faces many environmental challenges. Some are predictable and some are unexpected. To understand and solve problems, we need physical evidence that is systematically collected and logically analyzed. In summary, physical evidence systematically collected and logically analyzed helps scientists understand environmental issues, guide policy decisions, and find solutions. New research directed at finding a treatment for white nose syndrome is promising.